Okay, so today is our topic relation and functions. So without wasting much time, let's start it. So in the previous class, we study about the set theory, and in here we will understand what is the relations. Relation is a way of describing connections or associations between elements of one or more sets. The fundamental concept in theory forms the basis for many mathematical structures such as functions, equivalence relations, and order relations. So order relation. Now, so relation is very simple. In literal term also, what is relation? The association between two persons, the connections between two persons. Same way in mathematics, but it's for the two sets. What is an order pair? We will understand. When two elements, you can say, are coming together in the form of order. So an order pair which is written as A, B, like you studied in the Cartesian coordinate system, x and y are the combination of coordinate for any point on the Cartesian plane. So order pair is a pair of elements, right? First element, first coordinate, and the second element, second coordinate. So what are the features? The order of the elements matters, right? Because I already told you that when we have a Cartesian coordinate, so this is the value of x1 and y1, right? So x1, y1 will represent a different point. If we are taking like here x2, y2, okay. So you could take an example like suppose 2, 3 and 3, 2. So 2, 3 is different point and 3, 2 is different because 2, 3 saying that x value is 2, y value is 3. But when you are saying 3, 2, now here on x-axis value is going to be 3 and on y-axis value is going to be 2. So they matter. So features of an order pair is the order of the elements matters. Properties of order pairs. Order matters as mentioned earlier, A, B, B, A unless A is equals to B. So order matters when they are different, but when they are equal then order do not matters because 2, 2 is same as the 2, 2, right? This x and y, so their values are equal, so you do not have to consider the order that much. Equality of order pairs. Two order pairs are equal if only their corresponding elements are equal. So here if A is equals to C and B is equals to D, then we can say that the order pairs matters. So A, B not equals to B, E unless A is equals to B. Like example 1, 2 is not the same as 2, 1. And definitely 1 cannot be equals to 2. If they will be, then 2 is equals to 2 only. Cartesian product. So this is the symbol that we are going to use for the Cartesian products. How we will do the Cartesian product of two sets, we will see here. It's a fundamental concept in the relation function and graph theory. So definition of Cartesian product, if we will see, suppose we have a set A and we have a set B. So their Cartesian product is represented as A cross B. This is the Cartesian product. So Cartesian product. Okay, this is the representation. But how this will proceed? So it's saying that A and B will be in order. Okay, so one element from A will come, one element from the B will come. And A belongs to A and B belongs to the B. For example, you can see here 1, 2 and B x, y. So A is 1, 2 and B is x, y. So when you are doing the Cartesian product A into B, so first element of A 1 and the first element of B comes, then 1 and the second elements come, then 2 comes, then first elements comes. So you can take all the elements, but you have to remember that you are going to take the element in their ordered pair. Means first element comes from the A and then the elements come from the B. So each element of A is paired with each element of B. So this is all the possible relation, right? But if there is restrictions in the relations, then you have to define it in a different manner. So representations you already saw in the set. Right, same way set is a relation. Suppose we have two sets, so we can represent it in the sets. We have individual elements like 1, 2, 3, 4, A, B, C, right? But here we will talk about the relation. So relation is between two sets. Suppose we have a, so in roster form list all the order pairs. So we have A 1 2 3 and B 4 comma 5. So what is the relation going to be here? 1 4 1 5 2 4 2 5 3 4 3 5. So as I was telling that there is a restriction. So see this relation. Which type of relation? Where A should be less than B. If we will not consider A less than B, then there is a lot of possible relations. Like one can also go with the 4, one can also go with the 5. Okay. But our relation A should be less than B. So 3 4 and 3 5. So a small finite relation. Okay, but if suppose there is different condition, so that different condition will define the relation. Our condition here, A should be less than B. So we are making 1 with the 4. Okay, not 2 with the 1. Okay, and actually 1 is not here. So even in all possible conditions, this condition in this relation is satisfying. But suppose there is 1 2 3 and 5. Okay, even 5 is there in this element. Suppose 1 2 3 5 will be repeated. Suppose 6 is there. So we will not able to form the 6 comma 4 because this condition is violate A less than B. Okay, A must be less. So in this our set example, already all the elements of A is less than the element of B. So all the possible relations are coming under the condition. But suppose if we do not have A element less than the B, then we will not consider. So this type of element order will not come there. A small finite relations. So roster form is good for the small and finite relation, simple and clear, impractical for the larger and infinite relation. So if it's not suitable for the larger and infinite relation, so which type of representation is there? Set builder form. So relations using a rule or conditions determines. Like here we are representing A comma B. A is this element and B is the same example as previous one. So A belongs to A and B belongs to B, and A should be less than B. So this all you can see it's like in a proposition. It's an up like your an argument, and you can say what is this? A statement. Okay, so in the statement form like the in the set we did, but here is a relation. So you can say relation builder form. But okay, set builder form we are understanding that all the order pairs are here as a member of relation, and relation is a collection of the sets of order pair. So it's good for the larger relation, requires understanding of the conditions, maybe abstract sometimes because conditions can go on be like more than one components can be there in the relations and it becomes little complex. But okay, we can still represent in the our set builder form, right? Now then comes the arrow diagram. If we have a set A and we have a set B, then we can represent their relation. Suppose a relation is given here 1 4 1 5 2 4 2 5 3 4 3 5. Okay, so 1 is related to 4, 2 is related to 4, 2 is related to 5. So by the arrow diagram we will start from the set A. This is our set A and this is our set B. In the oval shape you can take, even in the rectangular shape you can take, and we will write the set A and B, and then we will by the help of an arrow we can show that which one is satisfying which relation, what is their outcome. So visualization of the relation can be better in this. It is intuitive and easy to interpret, but for larger and complex relation we cannot show. Then there comes the matrix representations. So pairs belongs to the relation, row corresponds to the elements of the first set, and column corresponds to the elements of the second set. So you can see here this A is representing your column and B is row side. So if we have elements of A 1 2 3 in our column and B 4 5 in our row, so 4 column 5 column you can say, the relation is 1 4. So 1 and 4 are related, so we are taking the value 1. If suppose 3 and 4 are not related in ours, can you see anywhere 3 and 4? No, in the relation we do not have 3 and 4, so we will represent as 0 because they do not have any relation. Same with the 5, 1 is related to 5, 3 is related to 5, but 2 is not related to 5 in this relation. 2 is not related to 5 in this relation, so we will represent here 0, and we will collect it in a matrix format 1 1 0 1 0 1. So this is the relation matrix for the relation. So it's finite relation, a small sets, useful for computational purpose, widely for larger sets. Then comes the graphical representations. Represents the relations as a direct graph. Digraph, we refer it as a digraph, where vertices are elements of the sets. So what are the vertices? Like all the elements of set A. Suppose a set A is 1, 2, 3, 4, and we are defining a relation on A, right? A on A relation, and we have the relation set is here 1, 2, 2, 3, 3, 1, 2, 4, 4, 4. So 1 is related to 2. So we will direct, right? We will direct the graph from 1 to 2. We will direct the graph from 2 to 3. We will direct the graph from 2 to 4. So all these relations are represented in direct graph. So it is called digraph. It's visualized connectivity, and definitely it's intuitive. Limitations not practical for very large sets. Okay. So till here we will keep this class. In the next we will show that what are the different types of relations. This is the representations, and we will see the different types of relation, and then we will understand about the functions. Okay. Okay, bye.